In this next example here, what we have is simplify as much as possible and write in terms of cosecant, secant, and cotangent x, then verify graphically. Again, verifying is going to be y1, y2. So here's our expression that we want to rewrite in terms of only secant, cosecant, secant, or cotangent. So what do I do here? So this is basically fraction plus another fraction. Well, in order for me to add fractions, I need a common denominator. So our common denominator, or what we used to call it as lowest common denominator, is going to be the following. So let's set up our lowest common denominator first. So my lowest common denominator LCD is going to be equal to 1 plus cos x and that 1 minus cos x. So I take a bit of both. So if I take both, I can rewrite this expression right away. The hint here, or the trick here, is sine x, the one on the left, it's going to be multiplied by this denominator here on the right. It's going to be multiplied by 1 minus cos x. And then we have, of course, that addition sign in the middle, and then you add another sine x up top there. It's going to be multiplied by this bottom left function. So we got the 1 plus cos x there. All of this is now going to be divided by the two denominators combined. So that's going to be 1 plus cos x in brackets and a 1 minus cos x. There we go. From here, what I want to do is try to distribute out and see what we get. So once I distribute out my numerator and denominator, I'm going to start with my denominator first because things cancel out really quickly there. It's a difference of squares, by the way. So this is 1, and this is going to be a negative cos x plus cos x, which will cancel out, and we have a minus cos squared x right there once we multiply the cos and cos together. In my numerator, what I end up with, and you got to do it very slowly, or at least be a bit careful here in our numerator. So our numerator, we have sine x, because that's sine x times 1, minus cos x sine x. So that's that there. Now we're on the second half here, so I'm going to go sine x times 1 again, plus another sine x, then plus this time cos x sine x. And notice that I went cos and then sine. I just go alphabetically usually. From here, I notice that I can cancel a few things out. I can cancel out my negative cos x sine x with this positive cos x sine x. Those would cancel out. Let's combine our two sine x's as well up top. So here we have our 1 minus cos squared x still there in the denominator, and now in our numerator we have our 2, because we're adding them together, 2 sine x's together. From here, I'm going to see if I can play around with some sort of identity. I do know one identity that would work, and it's basically pertaining to our denominator. I know that 1 minus cos squared x, if you look under your Pythagorean identities, that's the same thing as saying sine squared x. So let's quickly rewrite. So here, again, my denominator is now sine squared x, and that's coming from our Pythagorean identity. My numerator is still the same. We still have that 2 sine x in the numerator. From here, what I want to do is I can cancel out potentially a sine x numerator with a sine x denominator. So that's going to leave me with 2 over sine x. But again, if you read the original question, we don't want just sine x there. We want cosecant, secant, and cotangent. So I'm going to rewrite this. This is now 2 multiplied by 1 over sine x. So I just really quickly separated that. I know that sine x is the same thing as saying cosecant, so now I have 2 cosecant x. And there we go. That's going to be my final expression. We should check this on graphing calculator, and it did say be careful with how you type this in on your calculator. Be very, very careful. So I'm going to go y1, y2. Here we go. So in my y2 right away, I have 1 over sine x there. In my y1, I'm going to use my fraction function. If you don't have this, just be careful with the amount of brackets, but because I do have this option here, I'm just going to try my best to use it. Plus. And here we have sine x, numerator, and on this side 1 minus cos x. There we go. Again, if I go to my table of values, I'm looking for the same numbers, which we do have all along here. If I hit graph right away, and it will take a bit of time, but we should see overlap. And yes, we do. All my blue got overlapped with all the red. So we verified graphically, and that's perfectly fine. We're good to go. In the next example here, example 6, we have simplify as much as possible sine cubed x cos x plus cos cubed x sine x. Okay, so what can we do here? Well, there's nothing I can really divide out here, so what I'm going to do is factor out something. Let's factor out something in common in both. Well, I see cos x sine x in both. I can factor that out. If I factor out the cos x and sine x, what am I left with? Well, I'm left with, well, I already have one sine x here. I have 3 needed. I have sine squared x left over here. We're going to add on. Again, I factored out cos x, so I have 2 here. Took out that sine already, so I'm looking for cos squared x right there. So right away, I factored. From factoring, though, you can see or double check your Pythagorean identities. This sine squared x plus cos squared x is a Pythagorean identity. That's the same thing as saying just 1. So here we have cos x sine x, and that was multiplied by 1 because that was our Pythagorean identity. So we end up with just cos x sine x. And again, you could have just graphed this as all of this as y1 and cos x sine x as y2, and again, you're looking for overlap. And the next example says determine the restriction on tan x plus cosecant x. Okay, so restriction. The first one where we are restricting our domain between 0 inclusive to 2 pi not including. Okay, so first things first, let's rewrite this. So rewrite this so that we can try our best to figure out, well, what's in a denominator. Well, here I have nothing in a denominator, so really there's no restriction. However, if I rewrite tangent, tangent I could say is sine x over cos x. Cosecant, of course, is just 1 over sine x. So here, because I do have a denominator now, I need to set my NPVs. So on the left here, we got cos x cannot equal 0 there, because of course if you had 0 in your denominators you can't divide, so it can't equal 0. So when does cos x equal 0? That's when we're going to say cos x doesn't equal 0 there. We don't want cos x to equal 0. So x cannot equal at 9270, so that's pi over 2, and at 3 pi over 2 there. So x cannot equal pi over 2 and 3 pi over 2 on this first one here. On the second one here, sine x. Again, so we're going to say something along the lines of sine x cannot equal 0. So where does that occur? Well, when does sine equal 0? Well, we're at 0 at where sine is 0 at 0 degrees, and at 180, or that's the same thing as saying 0 in pi. So x here cannot equal 0 or pi. There we go. Those are all our restrictions between 0 and 2 pi, and again, we can't include 2 pi there. In this case here, our restriction is infinity, so we want to write down something in general so that we basically get to all of our restrictions. So for this first one here, because we already have it here, we're between 90 and 270, aka pi over 2, 3 pi over 2. I can say for cos x not equal to 0, we can say something along the lines of x cannot equal pi over 2 plus, well, from pi over 2 to 3 pi over 2, that's difference of pi n, where n is an element of an integer. Okay, so that's our first one. Our second one here, we have sine x cannot equal 0. So x truly can't equal, what do we have? So we have x can't equal between 0 and pi, so that's going to be, we can write x cannot equal just pi n, where n is an element of an integer. You don't really need to have 0 there. You don't need that 0 plus pi n. That's just overkill, but here that's going to be our expression, and then we're good for number 7. For number 8, determine the restriction on this identity. So restrictions, you're going to double check everywhere. Numerator, denominator, you check everywhere for the restriction. In this case here, we have a denominator. That means in our denominator, we want to say something along the lines of 1 plus sine x cannot equal 0, because you don't want a denominator of 0 there. So let's isolate for sine x. So I can say sine x cannot equal -1. Well, when does this occur? When is sine x equal to -1? Well, we're only equal to -1 in one position. So that's x cannot equal 270 degrees. And again, there's no mention whether you're in degrees or radian here, so I write down 270. And again, double checking my unit circle right there at the bottom. That's -1 on sine. That's again at 270 or 3 pi over 2. So whatever you want to work with. So I can say or 3 pi over 2. There we go. So again, it says determine the restrictions on this identity. There wasn't any domain restrictions, so let's just write down our restrictions in general so that we make sure that we hit everything. So really, we can say x cannot equal 270 degrees plus 360n. There we go, that's our first one. Our second one, of course, is if we did it in terms of radian, be 3 pi over 2 plus 2 pi n, where n is an element of an integer. There we go. So in this case here, again, there wasn't any restriction on our domain, so we want to write down general solution. So that we cover the gambit, we cover every single x values there. That concludes our lesson today. If you have any questions, please feel free to ask.